Have you ever driven past a modern construction site, watched workers stacking what look like giant white styrofoam coolers or flimsy pieces of lumber, and wondered, what on earth are we building? I've walked through hundreds of construction sites over the last 2 decades, and lately, almost every time I visit one, I get the same sinking feeling in my stomach. We are living in the age of the disposable home. While massive corporate volume builders are putting together cardboard-like boxes wrapped in plastic, house prices continue to skyrocket. We're asking people to sign away 30 years of their lives for a mortgage on a house that may begin rotting from the inside out within only a few decades. Think about that for a moment. Our ancestors constructed buildings like the Roman Pantheon, a structure that has remained standing for nearly 2,000 years through earthquakes, moisture, weather, and time. Yet today, one serious plumbing leak or a determined colony of termites can bring a modern suburban house to its knees. Many of our homes are essentially plastic bags. Moisture becomes trapped inside until the fast-growth softwood framing and structural OSB sheets underneath begin to swell, deteriorate, and rot. We are trading structural longevity for immediate corporate profit. But does it really have to be this way? Welcome back to Survival Roots. Today, we're taking a stand and looking at a quiet revolution happening in materials science. Technologies that already exist are already changing the way we build and are proving that homes can once again be designed to last for generations. We're exploring 12 breakthrough building materials that aren't simply more sustainable. They're smarter, stronger, and in many cases could save you thousands of dollars over the life of your home. Buckle up, because home construction is about to change forever. Chapter 1. The liquid stone that heals itself. Every homeowner knows this gut-wrenching moment. You're walking through your basement or checking the driveway when suddenly you see it, a thin, jagged crack running across the concrete foundation. Your stomach drops. Because you already know what might come next. Inspectors, contractors, repairs, and a massive bill. Concrete is the backbone of modern civilization, but it has one tragic weakness. Eventually, it cracks. In the United Kingdom alone, an estimated £40 billion is spent every single year repairing aging concrete structures. Across industrialized nations, material degradation and corrosion are estimated to consume an astonishing 3% of annual GDP. But what if concrete could repair itself while you sleep, almost like a cut healing on your skin? That is no longer science fiction. This is self-healing concrete, and it is already here. There are 3 primary ways scientists are teaching concrete to repair itself: bacterial systems, crystalline systems, and polymer microcapsules. In bacterial systems, or bioconcrete, pioneered by Professor Henk Jonkers at Delft University, dormant limestone-producing bacteria, such as Bacillus subtilis, are mixed into concrete together with a nutrient source, such as calcium lactate. The bacteria are protected inside tiny clay or leca pellets, so they can survive the extremely harsh and highly alkaline environment inside concrete. And here is the extraordinary part. Those bacteria can remain dormant inside a wall for as long as 200 years. The moment a microcrack appears and water begins entering the concrete, the bacteria wake up. They consume the calcium lactate and produce calcium carbonate, essentially limestone. That limestone gradually grows through the damaged area, filling the crack from the inside out and sealing it completely in roughly 21 days. If the idea of putting bacteria inside your foundation makes you uncomfortable, there is another approach. Crystalline admixtures, produced by companies such as Zypex and Penetron, are already widely specified in construction. When water reaches these chemicals inside the concrete, they react and form needle-like crystals. Those crystals grow into the empty spaces and can seal cracks up to approximately 0.5 millimeters wide. Then there are polymer microcapsules, which behave almost like microscopic containers of glue. When a developing crack ruptures one of these capsules, a bonding material such as cyanoacrylate, essentially superglue or epoxy, flows into the opening and hardens on contact. But where did this remarkable idea come from? Part of the answer was hiding in history. In 2023, MIT Associate Professor Admir Masic discovered that ancient Roman concrete contained white mineral inclusions known as lime clasts. The Romans used a process called hot mixing with quicklime, giving their concrete an internal self-repair mechanism. When cracks allowed water to enter, the water dissolved calcium from those lime clasts. The calcium then recrystallized inside the fracture, naturally sealing the damaged area. That helps explain why structures like the Pantheon remain standing, while so many modern concrete roads and structures seem to crumble before our eyes. Now let's talk about money. Is self-healing concrete worth the premium? Standard self-healing concrete currently carries an upfront cost increase of roughly 10% to 15%. Early bacterial versions were considerably more expensive, but as production scales, those costs are coming down rapidly. On a major infrastructure project involving a bus lane at Schiphol Airport treated with basilisk self-healing concrete, life cycle costs were reduced by 33%, CO2 emissions fell by 90%, and the expected service life increased by at least 15 years. For underground basements, water tanks, foundations, and other places where future repairs are difficult or extremely expensive, self-healing concrete can pay for itself in roughly 5 to 10 years, while delivering estimated whole life savings of 15% to 30%. Imagine having a foundation that repairs its own cracks before they become leaks. That is real peace of mind. Chapter 2. The Carbon Giants. Graphene and Synthetic Spider Silk. What if we could build homes and skyscrapers from structures 10 times stronger than steel while being 75 times lighter than styrofoam? To understand how that might happen, we need to enter the world of nanotechnology. Meet graphene, a material consisting of a single layer of carbon atoms arranged in a hexagonal lattice. It is the strongest material ever tested, yet it is remarkably lightweight and flexible. For decades, graphene remained largely a scientific curiosity trapped inside laboratories. But in recent years, engineers have begun finding ways to bring its extraordinary properties directly into the concrete truck. At the University of Manchester, engineers developed concretine, a graphene-enhanced form of concrete. By adding only a tiny fraction of graphene nanoplatelets to the concrete mixture, graphene acts like a microscopic catalyst. It accelerates the hydration reaction and helps create an extremely tight internal bond throughout the material. The result? Concrete that is roughly 30% stronger than conventional concrete. That additional strength allowed nationwide engineering to pour a 700 square meter floor slab for a gym in Wiltshire while using approximately 30% less concrete and completely eliminating steel reinforcement. Think about what that means. No rebar, 30% less concrete, and the result was a 25% to 30% reduction in CO2 emissions, together with estimated total construction cost savings of 15% to 20%. Yes, graphene itself costs more per gram, but because far less cement is required, and steel reinforcement can potentially be eliminated, the finished structure can actually become cheaper, while also being more durable. In Canada, BioGraphene Solutions is using organically sourced graphene to reduce cement requirements by as much as 25%, potentially offsetting hundreds of kilograms of CO2 for every concrete truck. And when graphene flakes are printed into three-dimensional forms under intense pressure and heat, they can create extraordinarily lightweight cylindrical structures that could theoretically support skyscrapers reaching heights of up to 98,000 feet. But this nanotechnology revolution doesn't stop with carbon. Now look at one of the most fascinating structural materials found in nature: spider silk. Spider silk is 5 times stronger than steel and 10 times tougher than Kevlar. Researchers at Cambridge University have successfully created synthetic spider silk. They produce it at room temperature from a hydrogel consisting of approximately 98% water combined with silica and cellulose fibers. Once that water evaporates, what remains is a fiber claimed to be 340 times more durable than concrete. Researchers are exploring its use in acoustic tiles, highly durable panels, and ultra-lightweight structural cables. Instead of depending entirely on heavy, carbon-intensive steel, we may be approaching a future where some building components are made from fibers spun from water and plant-based materials. How is that for radical innovation? Chapter 3. Grown, Not Built. The Mushroom Block Revolution. What if we stopped mining and manufacturing every component of our buildings and started growing some of them instead? What if, rather than firing clay bricks inside fossil-fueled kilns at temperatures around 2,000 degrees Fahrenheit, we allowed a living organism to grow a building block for us in the dark? Let me introduce you to mycelium-based materials. Mycelium is the dense network of branching, thread-like fungal structures associated with mushrooms that spreads through organic material. Scientists discovered that when mycelium is combined with agricultural waste, such as corn stalks, hemp herds, or even recycled coffee cup material, and placed inside a mold, the mycelium behaves like a natural, self-assembling glue. In only about 5 days, fungal threads spread into nearly every gap, binding the loose agricultural material together into a solid, rigid, lightweight block. The block is then dried to stop further growth. What remains is a strong, insulating, completely organic building material. To demonstrate that this idea could work at a much larger scale, architect David Benjamin and structural engineers from Arup constructed Hi-Fi, a 13-meter-high biological tower in the courtyard of MoMA PS1 in New York. They grew approximately 10,000 mycelium bricks, using agricultural waste supplied through innovative design. Throughout the summer, the tower successfully supported its own compressive loads. Then, at the end of the exhibition, something remarkable happened. The entire structure was dismantled. Instead of sending thousands of bricks to a landfill, the material was placed into compost. In roughly 60 days, the building returned to organic soil, with essentially zero landfill waste and zero carbon emissions. It became one of the clearest demonstrations that architecture could actually be designed to die. But practically speaking, could you build your permanent home from mushroom bricks today? Not quite yet. The biggest weakness of mycelium is water. If a mycelium block remains in direct contact with wet soil, decomposition can begin in approximately 6 weeks. But when these panels are kept dry and raised away from the ground, they can potentially last for up to 20 years, while providing thermal insulation capable of trapping more heat than traditional fiberglass. Mycelium is also naturally fire-resistant, mold-resistant, biodegradable, and does not release toxic formaldehyde. Commercial applications are already appearing in interior partition walls, acoustic dampening panels, and ceiling insulation. And the biological material revolution does not stop with mushrooms. To replace toxic synthetic plastics, companies such as Ricehouse are combining discarded rice husks with bioplastics and rock salts to create pressed wall panels designed to be highly durable, completely waterproof, and fireproof. Meanwhile, Japanese furniture pioneers are commercializing RiceWave, a structural bioplastic produced from inedible discarded rice. We are beginning to transform agricultural waste into high-performance, non-toxic building envelopes. Nature, it turns out, may be the ultimate manufacturer. Chapter 4. The Ultra-Structural Wood, Cross-Laminated Timber, CLT. For generations, we have constructed homes with stick framing, assembling relatively lightweight skeletons from fast-growth 2x4 softwood lumber and covering them with structural OSB sheathing. It is fast, it is inexpensive, but it is also fragile. And with lumber prices behaving like a roller coaster, the system is becoming increasingly difficult to justify as the only way forward. But what if we didn't have to abandon wood? What if we could engineer wood so that it performed more like steel or reinforced concrete while keeping only a fraction of concrete's carbon footprint? Enter cross-laminated timber, or CLT, the poster child of the mass timber revolution. CLT panels begin with solid wood boards. Those boards are laid flat and stacked in layers, with each layer running perpendicular, at 90 degrees, to the one beneath it. The layers are then bonded together using high-strength adhesives under enormous hydraulic pressure. This alternating grain pattern helps eliminate many of wood's natural weak directions. What comes out of the process is a massive, rigid structural wood panel, capable of carrying loads in two directions and delivering performance comparable to reinforced concrete while weighing far less. That lower weight means the building can often sit on smaller foundations, reducing both site work and concrete costs. But I know exactly what many people are thinking. It's wood. Won't the entire building burn down in minutes? Surprisingly, no. Because CLT members are so thick and dense, their behavior in a fire is very different from ordinary lightweight framing. When fire reaches the exterior surface, that outer layer chars at a predictable rate. The charred wood creates a protective carbon layer that reduces oxygen exposure and insulates the solid structural wood beneath it. That allows the interior core to remain structurally intact for hours. Lightweight stick frame houses can burn down in less than an hour, while mass timber structures can achieve fire ratings of up to 4 hours. That capability has helped make buildings such as Mycelium in Norway possible, a structure rising 18 stories without relying on a single steel column for its primary structural system. And now the regulatory landscape has reached a historic tipping point. The 2024 International Building Code, or IBC, introduced major updates that make tall mass timber construction dramatically easier and potentially less expensive. Under Type 4A construction, mass timber buildings can now reach up to 18 stories, or approximately 270 feet, provided the timber receives the required protective covering such as drywall. But there is an especially exciting change for builders who want the beauty of natural wood to remain visible. Under Type 4B, buildings can reach up to 12 stories, while allowing 100% of the ceilings to remain fully exposed, revealing the natural wood grain. And under Type 4C, buildings can rise as high as 9 stories, with exposed timber walls and ceilings, eliminating the need to cover those surfaces with drywall. This is not only about strength and safety, it is also about creating warm, biophilic living spaces while locking large amounts of atmospheric carbon directly into the structure of the building. Chapter 5. The CO2 Sponge, Hempcrete, and 3D Printed Resilience. Let's talk about a plant that can capture carbon at roughly twice the effectiveness of trees while reaching maturity in only about 6 months instead of 30 years. Industrial hemp. When the inner woody core of the hemp plant, known as hemp herds, is combined with a simple lime binder and water, the result is hempcrete, or more accurately, hemp lime. Hempcrete is not a load-bearing material. You cannot build your structural roof support directly from hempcrete. Instead, it functions as insulation and fire-resistant infill inside a separate structural frame. And in that role, it is an absolute superhero. First, hempcrete naturally breathes. Unlike modern buildings wrapped tightly in plastic layers that can trap moisture and contribute to mold problems, hempcrete acts as a natural humidity buffer. When indoor air becomes humid, the material absorbs moisture. When the air becomes dry, it releases that moisture again, helping regulate the indoor environment naturally. Second, hempcrete is highly fire-resistant. During rigorous ASTM E119 testing, hempcrete walls survive temperatures above 1,700 degrees Fahrenheit for more than an hour without significant heat transfer reaching the opposite side. And third, hempcrete is remarkably carbon negative. It can sequester roughly 40 to 50 kilograms of CO2 for every 100 kilograms of material. In other words, the walls of your house are literally helping clean the atmosphere. Hempcrete achieved a major regulatory victory when it was officially included in the International Residential Code in 2022 under Appendix BL, providing architects and owner-builders with a clearer legal pathway for constructing homes with the material. But what about cost? For years, hempcrete construction depended on slow, labor-intensive hand-packing methods. Now, however, Hempcrete is being combined with automated 3D printing, or 3DPH. A landmark economic study examined the cost of printing single-story hempcrete homes across 16 American cities. At first glance, the numbers are challenging. A 3D printed hempcrete home currently costs approximately 15% more than 3D printed concrete, 36% more than concrete masonry, and 52% more than standard lightweight wood framing. Why? Because the supply chain is still young, and hemp raw materials alone account for approximately 60% of total material costs. But the study did not stop there. Researchers examined what could happen by optimizing only 3 major design parameters. First, scale the supply chain and reduce raw material costs from $36.80 to $15 per cubic foot. Second, increase the printing nozzle speed to 12 inches per second. And third, use a 50% hollow infill pattern, giving the wall an infill area ratio of 0.5. Together, those changes could reduce superstructure construction costs by approximately 27%. Under those ideal conditions, a 3D printed hempcrete home would be only 17% more expensive than conventional stick framing up front, while becoming 11% cheaper than a comparable 3D printed concrete structure. And here is where the economics become even more interesting. Because hempcrete provides excellent insulation, homeowners can save thousands of dollars through lower utility bills over time. There are also major tax incentives. Under Section 45L of the United States Inflation Reduction Act, qualifying homes meeting Energy Star requirements can receive a $2,500 tax credit. If the home reaches the Zero Energy Ready Home, or ZER standard, that credit increases to $5,000 per dwelling. This is one reason FEMA and municipal agencies are examining 3D printed hempcrete as a potential approach for rebuilding resilient, fireproof, and hurricane-resistant housing inside the 483 designated Community Disaster Resilience Zones. It is the idea of a sustainable fortress that eventually pays you back. Chapter 6: The Air Conditioning Walls, Hydroceramics, and PCMS. What if the walls of your home could sweat in order to cool themselves, almost like a living organism? Air conditioning has kept our homes comfortable for decades, but those compressors consume enormous amounts of electricity and can send utility bills soaring. Scientists are now trying to change that equation with intelligent, climate-adaptive building materials. One of the most fascinating examples is hydroceramics, developed at the Institute for Advanced Architecture of Catalonia, or IAC. These wall-cladding panels combine traditional, inexpensive clay with embedded hydrogel capsules. Those hydrogel particles can absorb water equal to as much as 500 times their own weight. During rainy or humid conditions, the wall takes in water almost like a giant sponge. Then the sun comes out. As the exterior temperature rises, the stored water begins evaporating. That evaporation produces a cooling effect that helps lower the temperature inside the building. Tests have shown hydroceramic walls reducing interior temperatures by as much as 6 degrees Celsius, or more than 10 degrees Fahrenheit, while naturally increasing indoor humidity by around 15% in hot, dry environments. In other words, part of your cooling system is built directly into the clay itself. No compressor is required for the wall to perform that function. But cooling is only half of the problem. What happens when we want to store heat instead? For that, we have phase change materials, or PCMs. These materials can be integrated into drywall, plaster, or ceiling systems, where they absorb and release latent heat as they move between different physical states. During a hot day, when the room temperature climbs toward a predetermined threshold, say around 73 degrees Fahrenheit, the PCM, commonly made from paraffin wax or bio-based fatty acids, begins to melt. As it changes from solid to liquid, it absorbs a large amount of heat from the surrounding space, helping the room remain cooler. Then nighttime arrives. As the temperature falls, the material solidifies again and releases the heat it stored earlier back into the room. It behaves like a passive thermal battery, By continuously storing and releasing heat this way, PCMs can potentially reduce heating and cooling energy use by as much as 40%. No moving equipment, no mechanical humming, just physics quietly working inside your walls to keep the house comfortable. Chapter 7: Houses that Clean the Planet. Ferroc and Breathe Brick. Traditional concrete is responsible for roughly 8% of global CO2 emissions. But imagine building with a material that does not simply avoid releasing carbon. Imagine a material that actually absorbs carbon as it becomes stronger, and walls that simultaneously help clean the air entering your home. First, meet Ferroc. Ferroc is an environmentally focused alternative to conventional cement made from approximately 95% recycled industrial waste. The mixture combines iron dust, essentially steel waste collected from factories, with silica powder produced from ground recycled glass, along with water and lime. During curing, Ferroc does not simply release CO2 in the same way conventional cement production does. Instead, the material actively absorbs and traps carbon dioxide as part of the chemical process that causes it to solidify. That makes Ferroc a carbon-negative material. But here is the part that really gets people's attention. Ferroc is claimed to be 5 times stronger in both compression and bending than standard Portland cement concrete. Its unusual chemical structure also makes it highly resistant to saltwater corrosion, giving it enormous potential for seaside foundations and difficult marine environments. While the foundation beneath your home is absorbing carbon, the exterior walls could be doing something completely different, cleaning the air. That is the idea behind Breathe Bricks. Developed by Assistant Professor Carmen Trudell at Cal Poly, the Breathe Brick is a hollow concrete masonry block designed to become part of a building's normal ventilation system. Outside air enters through the face of the brick and moves into a miniature cyclonic filtration chamber inside the block. That cyclone spins the incoming air. Heavier contaminants such as dust and soot are separated from the airflow and fall into a removable collection hopper at the bottom of the wall. Meanwhile, the filtered air continues through the system and enters the building. Wind tunnel testing showed that this passive masonry system could remove 100% of coarse particles and approximately 30% of fine PM2.5 particles. It is almost like living inside one enormous passive air filter. And while the wall cleans your air, what if your concrete could also store electricity? Researchers at MIT have developed electricity-conducting cement. By adding carbon black nanoparticles to a cement mixture, they were able to transform ordinary concrete into an electrically conductive material. That opens the door to using the concrete structure itself as a massive rechargeable battery. By embedding an iron mesh anode and nickel mesh cathode inside the conductive cement, a foundation or driveway could become a structural battery storing approximately 7 watt-hours of electrical energy per square meter. That number may not sound extraordinary on its own, but consider how much concrete exists inside an entire building. Suddenly, the foundation beneath your feet becomes a giant energy storage system capable of holding solar electricity or operating a self-heating system that automatically melts snow from your driveway. We are taking material that once did nothing but carry structural loads and turning it into an active, energy-storing part of the home. Chapter 8: The Glass Killers. Transparent wood and ETFE windows are one of the largest sources of energy loss in any house. During winter, valuable heat escapes through conventional glass. During summer, solar heat pours through that same glass and turns interior spaces into greenhouses. Glass is also heavy, brittle, and expensive to manufacture. So what if we could replace some of that glass with something completely unexpected? Wood that you can see through. This is transparent wood. First developed at the University of Maryland, the process begins with thin sheets of natural wood, such as balsa. Those sheets are treated in a chemical bath using hydrogen peroxide to remove the lignin, the compound responsible for much of the wood's natural color. What remains is a clean, pale, hollow cellulose framework. That framework is then vacuum impregnated with a transparent polymer resin, such as epoxy, and cured using heat or ultraviolet light. The result is a sheet of translucent wood capable of allowing up to 90% of natural light to pass through it. But unlike ordinary glass, it retains the internal organic structure of wood. That structure makes the material 5 times stronger than traditional glass, far more resistant to shattering, and capable of providing dramatically better thermal insulation than conventional double-pane windows. And when this so-called nano-wood is pressed under intense pressure, it can become 30 times stronger than typical thermal insulation, creating an extremely tough, high-performance material for modern daylighting architecture. But sometimes, transparent wall panels are not enough. What if you need to cover an enormous roof, stadium, greenhouse, or atrium? Traditional glass can quickly become impractical. That is where ETFE, or ethylene tetrafluoroethylene, enters the picture. ETFE is a transparent polymer film that can be inflated into durable, cushion-like panels. It weighs only about 1% as much as glass, while transmitting approximately 95% of incoming light and still providing excellent thermal insulation. The material is extremely tough. It can withstand severe wind and snow loads, and its slick surface is naturally self-cleaning, allowing rainwater to wash dirt away. ETFE has been used on iconic structures such as Germany's Allianz Arena. More recently, it was used at Terminal 2 of Haneda Airport in Tokyo, where a film only 500 micrometers thick covers an area of approximately 9,000 square meters. Instead of requiring huge, heavy structural systems to hold sheets of fragile glass, ETFE allows architects to create enormous, airy, feather-light roofs filled with natural sunlight. And the transformation of the building envelope does not stop there. For exterior facades, traditional vinyl or metal siding can also be replaced with illusion panels, produced from stabilized aluminum foam. The process introduces air pockets into molten aluminum, creating panels that resemble metallic sponges. They are ultra-lightweight, completely fireproof, highly effective at soundproofing, and capable of creating a sleek, futuristic exterior that is virtually indestructible. Piece by piece, we are learning how to create building envelopes that are lighter, stronger, more energy efficient, and far better prepared to protect our homes from the elements. The era of the permanent home. We have just explored 12 incredible materials that are changing the face of construction forever. From SpaceX rocket engineers reinventing plywood, using perennial grass, to ancient Roman secrets helping modern concrete repair its own cracks, to entire building blocks grown from mushroom roots in only 5 days. The technology needed to create homes capable of outlasting your children, your grandchildren, and even your great-grandchildren is no longer some distant dream. It is already here, right now, in 2026. But as someone who believes deeply in sustainable, self-reliant living, I also have to be completely honest with you. Building a permanent, high-performance home like this involves one major strategic trade-off: future flexibility versus permanent strength. Traditional stick-frame homes survive partly because they are flexible, or perhaps more accurately, because they are temporary enough to change easily. If you decide 20 years from now that you want to remodel the kitchen, install another electrical outlet, or cut a completely new window into a wall, the job can be relatively simple. Grab a drywall saw, grab a handsaw, and in an afternoon, you can begin changing the house. But when you build with steel-reinforced concrete, conductive cement, thick insulation, and other high-performance systems, you are creating something very different. You are creating an airtight, monolithic bunker. If 20 years later you decide that a wall needs to move or a new window needs to be cut through the structure, a handsaw will no longer be enough. Now you need a concrete saw. You need a jackhammer, and you may need a structural engineer to recalculate the loads before you begin cutting into anything. That is the trade. You give up some future flexibility in exchange for permanent, almost indestructible strength. But when you examine the economics over the entire life of the building, the answer becomes much clearer. A comprehensive multi-criteria decision-making and life cycle assessment framework shows that advanced hybrid geopolymer biofiber systems, known as H1 and H2, can reduce carbon emissions by approximately 36% to 45%, while cutting 19% to 28% from the total 50-year life cycle cost of ownership. The higher initial investment can be recovered through operational savings in only about 4 to 7 years. So I want to leave you with one question. What kind of roots do you want to plant? Do you want to spend decades paying off a disposable, plastic-wrapped box that may begin deteriorating before the mortgage itself is finally paid? Or do you want to plant something deeper, something stronger, something resilient enough to become both a physical and biological sanctuary, a home designed to protect your family from wildfires, hurricanes, energy crises, and the pressures of time for generations to come? The choice is yours. Let me know in the comments below which of these 12 materials you would most want to use in your future home, and tell me why. I read every single comment. If you found this video valuable, hit the like button, share it with someone who loves building, and don't forget to subscribe to Survival Roots for more deep dives into resilient, sustainable living. Until next time, stay strong, stay resilient, and build for the future.